All right, hello class. Moving right along, we are now at lecture 11. Those of you still following along will have seen that we have moved deeply into our discussion of linear dynamical phenomena, having worked out a time-dependent linear response theory in the last couple lectures, both classically and quantum mechanically. And what comes out of that discussion is a notion of, or is an importance played by time correlation functions. So specifically, we set up our response theory such that we envisioned having a Hamiltonian which determines both the energetics of initial conditions and thus the initial conditions from a Boltzmann distribution, as well as the dynamics of a system that was decomposable into a reference part, something that we understand very well, and some time-dependent force acting conjugately to A, some arbitrary observable, provided that we could ask questions, say if we turn that time-dependent force on at time is equal to 0, we could ask how A evolves in time. Having driven the system away from equilibrium, observables like A will now obtain a time dependence. They are no longer stationary, since the system is no longer stationary, having been under the influence of this time-dependent force. So in general, A will deviate from its average, which it would have under that reference Hamiltonian. And we worked out exactly what that deviation is, at least in the limit that F is small. We can Taylor expand and note that the influence of F to first order is mediated through a response function, just as we had found statically. So that chi, that response function, encodes how the influence of F changes the average value of A in time. And in the last couple lectures, we noted that because it must encode time dependence, it depends on the underlying equations of motion in general. And we found that we got different answers if we treated the dynamics classically, in which case chi at some point in time t is given by a scale set by thermal energy, beta, a factor that invokes causality, this step function theta, which says that F shouldn't influence A in the past, only in the future. The canonical way of writing chi is under that integral. In reality, we find that chi proportionally determines the response of A, so this time derivative would pull it out of the integral. And just like we found statically, the response of a perturbation is proportional to the fluctuations of the system in the absence of that perturbation, here encoded in a time correlation function between A at time 0 and A at time t into the future. What changes quantum mechanically is that we don't ever know exactly where the system starts. The origin of time, in some sense, is uncertain. And so rather than correlating A exactly at 0, we can encode that uncertainty in an integral over imaginary time, whose scale is beta h bar in size. So in the limit that h bar goes to 0 or temperature goes to infinity, those are classical limits. That domain of that integral shrinks to a point, time is equal to 0, and we recover our classical result. Okay, so this is to remind you just how important these time correlation functions are, because they encode the full response of a system. This is true for arbitrary f. As long as f acts conjugate to a, I could have the time dependence of f be sinusoidal, a step function, a delta function, any complex dependence. As long as f is small, the response will be satisfied by this linear response relationship. So that motivates then a discussion of how we should try to approximately solve for time correlation functions. How should we model time correlation functions? We saw in the last lecture that in principle they are measurable. The imaginary part of this response function is an absorption spectrum. You'll work out the quantum mechanical analog and find that that still is true. So we can measure it, and we know that they encode molecular dynamics. It sure would be nice if we could model it. And so what we're going to undergo over the next few lectures is analogous to what we did in the static case. So statically, we found spatial correlation functions in code response. And then we built up a theory of spatial correlation functions within our Gaussian field theory. We posed that the system fluctuated in a strictly Gaussian way, and that let us solve for correlation functions. And we'll do the same thing here. Though here, we'll need to, from the onset, develop a description on the dynamics of the system. And so rather than a Gaussian field theory, it will be natural to discuss the modeling of time correlation functions within a class of so-called linear dynamical models. The first of which we'll derive today. So again, our goal is to develop a theory from which we can then approximately compute time correlation functions. Okay. So what I will show you envisions a somewhat simple case in which we imagine that we have a bunch of particles composing some solvent. And they interact with a bigger particle, some big solutes. And what we're going to try to understand is the time correlation functions of that solute and how they are encoded by the fluctuations of the solvent. And specifically, what we will try to do is to completely get rid of the dynamical description of the solvent, integrate out its contributions to the equation of motion of that solute, and thus get an effective equation of motion for just this tagged particle. So we'll go from a description on the left, where we have lots of interacting degrees of freedom. Let's call the set of coordinates from the bath y's. The tagged position of our particle that we are interested in, x. And we will try to get an effective equation of motion that we could solve, a one-dimensional equation that we can hope to solve exactly, having gotten rid of the complexity that makes solving the equations of motion and therefore time correlation functions in this interacting many body system difficult, namely all of those extra solvent degrees of freedom. So the way that this will proceed is not incredibly general. There is a much more general way to do this, but it involves some more complicated mathematical operations. Those who are interested can go and look in Zwanzig's non-equilibrium statistical mechanics book and learn about so-called projection operators, which will allow us to do this integration over the solvent degrees of freedom in a very general way. But the derivation I will show for this effective equation of motion for our tagged particle gets essentially to the heart of the approximations that are made. So I think it's sufficient for this class. Okay, so this is what we want to do. We want to take a complicated interacting system whose specific trajectories we can't hope to actually solve for due to those interactions, boil it down into one degree of freedom that we're interested in, and thus have a potentially simplified equation of motion that we can compute things like time correlation functions over. So this specific development, trying to model the motion of a single tagged particle in a solvent, will give us, at the end, a so-called Langevin equation of motion. So that'll be the result that we'll get to at the end of this derivation. Okay, so let's start by envisioning that we have a Hamiltonian that we can decompose into a part that just depends on that solute degree of freedom, so our tagged particle, plus a Hamiltonian that just describes those solvent or bath degrees of freedom, the y variables, plus a piece that tells me how those two interact. So let's, for simplicity, assume that that interaction part of the Hamiltonian, the way in which the solute interacts with the solution, is through a linear coupling, namely the dynamical degree of freedom for the solute X acts on the solvent particles, the Y's, through some constant interaction scale, I. So this is the sort of thing which is appropriate if the displacement of the Y's are not too large, if the interaction is not too strong. We have this linear coupling between the system and the bath, the solute and the bath. So this, of course, must be an approximation. In general, solutes and solvents will interact through much more complicated interactions, but we are envisioning that we can linearize those, that the scale is such that either the interaction strength or the corresponding displacements are small in some sense. Now this bilinear form, linear in both x and y, then is clearly in the class of problems that we've been studying over the last couple lectures. We can imagine a reference, which is our H naught plus the HB, the Hamiltonian for the bath, plus the Hamiltonian in the solvent in the action, in the without an interaction. And we can imagine perturbatively including that interaction term and solving for the implications on the equations of motion of that interaction. So let's assume that at time 0, the solute is at the origin. Then the harmonic degrees of freedom, these Bath variables that we are going to assume are harmonic, can be integrated exactly. Each harmonic degree of freedom, y, at a time t, will be whatever that y is in the absence of the coupling to the solute, plus treating that solute interaction as a perturbation, we know that we will get an integral over a response function. And then the force corresponding to this interaction given by the gradient of v with respect to yi is just x ai like so. So again, here is the trajectory without coupling to the solute. Here is how the trajectory evolves with that coupling. And if these y degrees of freedom really are harmonic, if their fluctuations are Gaussian, we actually know what the correlation function is already. We worked that out a few lectures ago, what the response function is for our harmonic oscillator system. Specifically, chi, yeah, I think I missed minus signs up at the top of this lecture. Sorry about that. Canonically defined with a minus sign, is minus beta, that step function, d dt, and now a correlation function. If I'm acting linearly on the y's, then that correlation function is yi at 0, yi at t. So we can further assume that these harmonic degrees of freedom have equilibrium positions where y on average is just 0. So we can take this expression for how the Bath degrees of freedom evolve in the presence of the coupling, which, again, if these are harmonic degrees of freedom, would be exact. So to the extent that their fluctuations are Gaussian, this is exact. And we can rewrite it having introduced this chi parameter, this response function. So specifically, yi of t in the presence of the interaction is yi in the absence of the interaction. First plugging in our response function, beta's constant, comes outside. An integral over time. That correlation function evaluated at t less t prime, ai xi. And now I can either act that time derivative on the correlation function, or I could integrate that by parts and act it on x. Again, a is just a constant. And I will, in general, have a boundary term that results. There's no reason that that is 0. Coming from Ci at t is equal to t prime and xi also evaluated at t. So there's only one boundary term here because I've assumed that x at 0 is 0. So I evaluate that integration. In doing integration by parts, I evaluate that boundary term at t is equal to 0 and t is equal to t. The former with x is equal to 0 goes to 0. The latter evaluates x at t and c at t minus t prime, therefore at 0. Okay, so this is an equation of motion for the Bath variables that we're assuming respond linearly. We could analogously write down an equation of motion for now our solute. So starting from the beginning, we know it's a classical particle, obey a Newtonian or Hamiltonian dynamics, in which case the acceleration on the particle, if it has mass m, is given by a gradient of the potential that that particle might feel, which would be in this reference part of the Hamiltonian of just the solute. But in addition, there's a force acting on it from the bath, which is a sum weighted by the AIs of linear forces from each bath variable. So now, note, this is the yi's are in principle time dependent, and we have just solved for what their time dependence is. It's given through this linear response relationship right above. So we can plug this whole thing in to our equation of motion for the solutes and arrive at that the acceleration depends on the gradient of the potential that the solute feels in the absence of any solvent, plus I have a sum over all the variables weighted by AI, and now the reference part of the trajectory of AI, so the yi's, how the y's evolve in the absence of the interaction between them and the solute. I have a minus, a beta, an integral over those y correlation functions. But that depends on the acceleration, or on the velocity of the solute particle. And plus this boundary term that depends on the position of the solute particle. So wrapping this up, or simplifying it, I have some reference force on the solute. I have plus beta Ci at 0 AI squared x of t. That's from this term. I have a sum over AI yi in the reference. And finally, I have a minus beta and an integral over time, the response function of the bath, on the velocity of the solute particle. So this is a now closed expression for the motion of the solute particle. It's a complicated one. It depends on aspects of the bath, but we have gotten rid of the dynamical evolution of the bath itself. So there's nowhere in this equation of motion that requires us to simultaneously solve the equation of motion for the bath and that of the particle. Let's go ahead and rewrite this one more time to simplify it even further. So let's identify CB as a total correlation function of the bath. So it is the correlation for each individual oscillator, weighted by how strongly that oscillator is coupled to the solute, the A variables. So this encodes the total weighted correlation function from the bath. Let's also define the first two terms, which don't have any dependence on any time dependence other than through x. Let's define some w of x as our original potential less beta by 2, the bath correlation function evaluated at 0, x squared. So if we take a minus a gradient of that, we will get this force, and we will get this additional force that acts linearly on the solute. So what we see here is that this W acts as a renormalized potential to renormalize the potential that the solute originally evolves in. In general, we know that that's true. We've seen already in previous lectures that if we integrate out some degrees of freedom, we generate effective interactions manifesting or representing the correlations that those interactions have between the remaining particles. So this is essentially a manifestation of a potential of mean force that would tell me how this solute interacts with other solute molecules or with other objects that I haven't integrated out as mediated through these bath degrees of freedom that I have gotten rid of. So let's keep going. This third term here, well, that is independent of the system. It is itself time dependent, but it depends only on the bath degrees of freedom, not on the solute. So let's define some time-dependent force, R, as a sum over all those coupling strengths in these original trajectories of the solvent. So this is something probably complicated, but it's not dependent on the solute. Depends only on this is a force summed over all those bath degrees of freedom, independent of what the solute is doing. And if n is very big, we might imagine that this sum has a central limit theorem, in which case R, acting as the sum over those random variables, if n is large, might itself be expressible as a Gaussian random variable. So again, this is some complicated fluctuating force independent of the x's, dependent on the y degrees of freedom, but if they're harmonic, we could go to some normal modes, in which case they are uncorrelated. If n is large, I have a sum of uncorrelated random variables. So we have every reason to expect that to a good approximation, R is some Gaussian random variable, at least near its mean. So let's finally identify a function gamma of t, which is equal to beta times that total bath correlation function by 2, which is the last term. I have a beta, sorry, this has a sum over i's in it. And those should have been squared. I have one from here and one from here. So that is indeed up to a factor of beta. the total Bath correlation function lying under that integral, acting on the velocity of the particle. So now written in terms of these variables, the renormalized potential, the fluctuating Gaussian random variable in this gamma function, we find an equation of motion for the solute equal to the derivative of the potential of mean force, the renormalized potential having integrated out the Bath, minus twice through this definition of gamma, an integral over time, this gamma of t less t prime, x dot of t prime, plus r of t. So this is a fundamental result. So let's highlight it. This is known as the generalized Langevin equation. And it's really interesting. It says that if we were to follow only our big solute particle and not be concerned with the motions of the solvents around it, so we integrate out those solvent degrees of freedom, their dynamics, the effective equation of motion that we find is first a renormalization of the original potential that the solute moves in. That's a static contribution. That's the same sort of thermodynamic consequences we've seen previously when we integrate out degrees of freedom. But more interestingly, we found first that the equation of motion is no longer deterministic. This R variable is stochastic. It's a random variable as a function of time. And it's also not time local. If in a Newtonian trajectory, a Newtonian system, I give you local in time information, like where the particle is and how fast it's going, I can predict the trajectory that that particle traces out. That is no longer the case here. This convolution over this gamma function time with the velocity of the particle tells me that the trajectory of the particle depends on times in the past through this gamma function, as weighted by this gamma function. The fact that it looks like minus gamma times x dot should give you some intuition that this is like a friction. It's a friction that has time dependence. We would also say that this is a friction that gives the solute a memory in its dynamics. Memory because the trajectory that that particle traces out depends on times in the past, on the memory that it carries around with it from its time evolution back as far as there is support in that gamma function. To understand this more carefully, we need to understand exactly what the statistics of these random forces are. We know that we've argued that it's a Gaussian, but what are its mean and variance that will uniquely determine that Gaussian random variable. Well, on average, R of t, which is given by a sum over ai yi at 0. Well, we've assumed that these are harmonic degrees of freedom that do not have an on average position. And so this force on average is 0. Indeed, that should make a lot of sense. If that force had a finite mean, that would cause the particle or solute to move in one direction over another. That doesn't sound very much like an equilibrium system. That's essentially a consequence of translational invariance, saying that I could have centered those harmonic degrees of freedom anywhere I want. The variance of this fluctuating quantity R is then given by squaring that sum and averaging it. So these are uncorrelated harmonic variables, so I can assume that their cross terms go away and I'm left with ai squared yi naught at t yi naught at t prime. If I bring those averaging operations inside, get I get ai squared yi naught of t yi naught of t prime. Well, that's a correlation function in the yi's. Summing over all of them, that is exactly what I defined as my total Bath correlation function. And if we remember, we have defined this gamma function, this friction, as proportional to that Bath correlation function with a constant of proportionality, which is twice kBt. So what we've just found is that the fluctuations of that random force are exactly equal to the temperature times the friction that acts to oppose the particle's motion. So the friction and the random forces are exactly balanced to encode the temperature of the system. Indeed, if I had a friction that only dissipated energy, the energy of that solute particle would continue to go down. There would be nothing left to restore energy flow back to the particle in order for it to develop a Boltzmann distribution where different energies should be observed based on its Boltzmann probability weight. So we find naturally that a temperature is introduced by this balancing of a frictional force, a dissipative force, by a random force that acts to add energy back in. So again, the bath takes out energy through this friction and puts it back through a random force in such a way that there's no net force moving the particle around, but just an ability to transmit energy back to it. And that balancing encodes the temperature. And this result, this balancing, is often known as the second fluctuation dissipation theorem. As a microscopic manifestation of what we typically think of as a more macroscopic response relationship. So this equation, and specifically this development, imagining the bath as harmonically responding, was initially derived by Robert Zwanzig. And it was generalized using much more complicated mathematical techniques that let one move away from strictly harmonic oscillators to more complicated interactions linearized about those typical values by Massimo Mori. And so for this reason, the development of this sort of generalized Langevin equation is often referred to through the Mori-Zwanzig formalism. So we can think about a couple limits of this pretty complicated equation. This generalized Langevin equation, which is non-local in time, and for which we only, again, maybe we should emphasize this, that we can, in principle, solve this equation, provided only that total bath correlation function and the original force that the solute is experiencing. So there's a parameterization that depends on a correlation function of the bath in this case. So one thing one would like to do is to return the time locality of this equation to get rid of that convolution under the time integral. So rewriting that here. One limit we can take would be to assume that the bath relaxes very quickly. In which case its correlation functions decay very quickly. If they relax infinitely quickly, that friction would go to just a delta function. This is a so-called Markovian approximation. Inserting that into the equation of motion restores its time locality. That delta function lets me kill the integral. Like so. And the boundary term I get by having that delta function only be represented as half of that delta function is what kills that factor of 1/2. So this is what is typically known as the regular Langevin equation. In that I have a simple time-independent frictional force balanced by the random force, since making the Markovian approximation doesn't change the fact that the fluctuations of that random force still have to be balanced by that friction. There's one additional limit often discussed, and the limit that that solute particle is really, really big, such that it interacts with lots of bath particles, and thus the friction on that solute is large. So if the friction is very large, the inertia we can assume to be small. This is a very low Reynolds number approximation. In the limit that the inertia can be set to exactly 0, we can then solve for an equation of motion that depends only on the velocity and the position of the particle, which then looks like that. This is often referred to as the over-damped Langevin equation. Damped because the friction is large. It is the equation of motion for Brownian motion. In the absence of a potential, in the absence of that W function, that potential of mean force, this tells me that the way the particle moves around in space is just given by those random forces. So this equation here has a long history. It was first invoked by Einstein in one of his famous 1905 papers, the paper on Brownian motion, which is really a joy to read. There are versions of it translated from its original German that you can find online, in which Einstein essentially intuited this same sort of structure, that if I have a big particle, it has no inertia in a solvent because of the high viscosity of that solvent. And if I imagine that the solute or the solvent particles act in a random way as a sum of a bunch of random forces, then he modeled those fluctuating forces as a Gaussian process. And thus the formalism of Brownian motion was invented. This was in order to make sense of observations of botanist Robert Brown, who in 1827 was the first to observe that pollen grains in water underwent an erratic motion. One of the coolest things is that those fluctuations of the forces encode Kb, Boltzmann's constant, which we know is related to the ideal gas constant through a constant of proportionality known as Avogadro's number. Indeed, it was the measurement of Brownian motion that let Einstein estimate the size of Avogadro's number in a way that was much more accurate than previous estimations had been. Okay, so that's the two limits, common limits of the Langevin equation. I want to show you how this actually manifests in an actual simulation. Okay, so we can actually get a sense for the applicability of this Langevin equation by actually showing you how random a motion of a particle really does look. So what I'll do here is I'll take this molecular dynamics code that we've run a couple times before in class, and I will visualize it in two different ways. I will show you a visualization in which all particles are present, and I tag a single particle and watch by tagging it in a different color, you'll be able to watch it evolve in time. And in a second representation, shown in a second on the right, you'll see just that tagged particle. And while on the left you'll be able to note the specific causal properties, the specific causal events that cause the motion of that particle to trace out its specific trajectory, the bumps and collisions that cause it to change direction or to increase its velocity. If you just follow the particle on the right in the representation without that path, it should be clear that it undergoes a fairly simple process that is, though, random. But provided we can encode the statistics of that random process through a friction and a random force, we could arrive at an effective equation of motion. So let's see how this would work. Let's run the simulation. So here is the system without all of the other particles. Following that tagged particle and the one on the left is the same simulation, just showing you all of the other particles that it's interacting with. So on the left, you can see the individual bumps and collisions that give rise to specific motions of that tagged red particle. But if you follow the particle on the right, it looks like, for all intents and purposes, it's undergoing a simple random walk process. Here, the size disparity in the frictions are such that it's not completely overdamped. So there is some momenta, there's some inertia. Nevertheless, that motion looks pretty random. And if I was to actually compute the statistics, which I would encourage you all to do, you would find that the displacement statistics are Gaussian. In fact, we have already argued in our discussion of a Green-Kubo relationship that the long time limit is of the mean squared displacement of the particle. So there's no external potential acting on this red particle. So it should evolve freely in the absence of those solvent blue particles. That mean squared displacement is a Gaussian random variable. It has a variance that grows with time, reflecting uncorrelated fluctuations of that particle's velocity. Okay. So let's go back here to notability and continue on. We can actually now encode or decode the velocity autocorrelation function. You'll model that function within this Langevin framework. So let's apply this Langevin equation of motion to understand a velocity autocorrelation function. So let's set this potential to 0. So there are no net forces acting on particles. And let's set the mass of our tagged particle to 1. The generalized Langevin equation tells us that the rate of change of the solute particle's velocity is equal to minus twice this convolution of a friction kernel with the velocity plus some random variable, random force. Let's take this equation of motion and multiply the left and right sides by the initial velocity. So the initial velocity is independent of time, so it can go under that time derivative. It can go inside the time integral. Like so. And now I could ask for its average. Again, a linear operation commutes with differentials. like so. So now this gives me an explicit equation for the time dependence of the velocity-velocity autocorrelation function. Specifically, replacing that definition, I have the rate of change of that velocity autocorrelation function is equal to minus 2 this convolution of the friction kernel with that correlation function. And this quantity here, the average of V with that random force in the future, is identically 0. Again, those random forces are the forces of the bath in the absence of any solute interaction. So those can't be influenced by the velocity in the past of that solute. And so now we have a closed expression here for the velocity-velocity autocorrelation function. We can solve this equation using Laplace transforms. If we Laplace transform both sides, so we have a time derivative, so we use our usual trick of noting that there's an exact Laplace transform of time derivatives, which gives me that Laplace variable times the function in Laplace space less its initial condition in real time. We can use the convolution theorem to pull out the Laplace transform of the friction kernel and independently the correlation function. In which case now we have a simple linear equation, algebraic equation that we can solve, giving us that the Laplace transform of the time correlation function is just its initial condition in real time divided by s times twice the Laplace transform of the friction kernel. And this is true for any friction. So provided a friction, a time-dependent function whose Laplace transform exists, we could plug it in and in principle solve for the velocity autocorrelation function. Specific examples that are tractable would be, for example, the Markovian limit. So if we take gamma of t to be gamma by 2 delta t, that's just a constant. We would find, inverting that Laplace transform, that c of t is equal to c of 0 and a decaying exponential with a rate that depends on that gamma. So in the Markovian approximation, we find that velocity correlations are exponentially decaying. Recalling our, let's clean that up. Recalling our Green-Kubo relationship, the diffusion constant being equal to an integral over the velocity-velocity autocorrelation function. plugging that in. So C0 is the mean squared velocity on average, which is just kBt. Again, m is set to 1. We have an integral over this decaying exponential, which just gives us kBt over gamma. If we were to model what that friction is in a solvent, say a solvent with a given viscosity mu, if the solute has a definite size r, then Stokes' law tells us that the friction of a sphere of size r in a solution with viscosity mu is 6 pi r times mu. That's solvable using a different sort of theory Navier-Stokes, hydrodynamics, finding the total frictional force acting on a sphere dragged through a fluid. If you put this together, you find that D is equal to kBt over 6 pi r mu. This is known as the Einstein relationship, or the Einstein-Stokes relationship. And indeed works actually incredibly well, even for R's that are nanometers in scale, even for R's that are angstroms in scale. Stokes-Einstein actually tends to work even to predict the diffusion constants of individual atoms evolving in a solution of similar particles. However, this Markovian approximation is not so good for systems that are, really molecular and really dense, in which case the bath does not relax infinitely quickly. So for systems like a colloid moving around in a solution, you can really get quantitative accuracy with the Stokes-Einstein relationship. You can't quite get quantitative accuracy when you scale that all the way down to a molecular fluid. That is essentially because for a molecular fluid, if we were to look at the velocity-velocity autocorrelation function, it looks a bit like that. Which has much more structure than a simple decaying exponential. And most notably, it has this recoil which has a simple physical interpretation. If I looked at a particle as it's moving around in a dense solution, if it had some initial velocity pointing in that direction, well, it might bump into one of those dense other particles and become anti-correlated in its velocity immediately after that collision. So that recoil is manifesting that dense environment, in which case there's enough room for a particle to inertially transition forward and then be knocked backwards. So in this case, the Markovian approximation breaks down, so we need to build in some amount of memory into the system. And a very simple model of a solution or a friction system with memory is to assume that that the friction isn't Markovian, but that the memory is localized in time. So a typical model for the friction is some exponential decay with some characteristic scale, gamma, and some characteristic time, call it tau b. So this is a simple model in which case there's one time scale to the bath, tau b, and one characteristic friction value, gamma. Now, if we know the Laplace transform of this function, which we do, it's just simple exponential, we can put that Laplace transform back into our solution for the velocity-velocity autocorrelation function in Laplace space. Like so. And now we just require that we can invert that Laplace transform. We can note that it has an interesting sort of structure. This continued fraction structure where in Laplace space, the velocity-velocity autocorrelation function is a fraction of a fraction. That sort of continued fraction form is universally found in systems with memory. In fact, it has become very popular recently to write down quantum dynamical approximations in this kind of continued fraction representation. This is essentially a way of bootstrapping your way up to an exact description of an open quantum system. More on that in a few lectures in the future. But it is known for the experts, people interested in these sorts of things, as the hierarchical equations of motion. It's essentially this sort of procedure just for a quantum memory function instead of a classical memory function like we're dealing with here. That being said, this form can be Laplace, inverse Laplace transform. Which yields a C of t is equal to C of 0 times a sinusoidal function, a cosine function, plus a sine function with frequencies omega bar and scales 1 and twice tau b omega bar, with an envelope which is itself a decaying exponential, where this omega bar is 1 over 4 tau b squared. So this is actually a very good model for a dense liquid. like the simulation I just showed you, there will be some memory due to those collisions. And parameterizing that memory with a simple time scale is sufficient to then pretty accurately predict or model the velocity autocorrelation functions and therefore the diffusion of solutes in solution. Okay, so taking a step back, what have we just learned? So we have just found that, having noted that time correlation functions are important for determining the time-dependent response of a system, it behooves us to try to figure out how to model time correlation functions, and this is one very successful route to that. Namely, we know that in principle, if we can evolve the dynamics of a system, we could compute time correlation functions, but for any interacting system, solving the coupled ODEs that are Newton's or Hamilton's equations of motion is complicated and impossible, intractable in most cases. So rather than try to solve them all simultaneously, we imagine trying to solve for just the ones we care about, just some set of degrees of freedom, tagged particles, or the solute in this case, and explicitly integrate out all of those other variables, assuming that they respond linearly. So we employed our notions of linear response on the microscopic scale to get this model for time correlation functions, or for generally the dynamics of a system weakly coupled to its surroundings. Now, this weak coupling can manifest in different sorts of ways. Either it's you can envision a big particle moving around in a solvent made up of much smaller particles, in which case the big particle on an individual solvent interaction is weak as it's spread over a number of different solvents. It turns out, as I've alluded to, that there is an exact expression of the generalized Langevin equation that doesn't make that assumption, but which is not itself closed. To close it, one could, rather than explicitly imagining weak coupling, imagine that the fluctuations of the solvent are Gaussian. If they're Gaussian, they will always respond linearly, and so there's a large domain for which our response theory would be valid. And indeed, as we've already seen in the context of density fluctuations, at least statically, that Gaussian approximation is very good. To the extent that dynamical quantities in complex systems are sums of many complicated, though finitely correlated fluctuations, we should expect from the central limit theorem again to flow to a description in which Gaussian statistics is valid. Having done that, we worked out the generalized Langevin equation, a time non-local expression for the equations of motion of our reduced system, and talked about a few explicit limits, like the Langevin equation under the Markovian approximation, where the bath relaxes quickly, or the overdamped limit, in which we get an equation of motion for Brownian motion. And now we've just shown explicitly how we can use that information to actually predict time correlation functions, to model them in a fair amount of sophistication, either in a Markovian limit, in which case they just decay exponentially, or in a non-Markovian limit, in which case the bath has a finite memory and we get more complicated correlations. All right, so that's all I have for today. I'll look forward to seeing you all in the small group discussions, and hope you all are doing well. All right.